In this video, I'm going to talk about angular momentum. I'll start with some theory and then give some example questions. Read the success criteria I plan to cover. Just like my other videos on rotational motion, let's do the comparison between translational motion and rotational motion. So translational motion would be like moving in a straight line. And if I'm talking about momentum, we would use the equation momentum equals mass times velocity. So traveling in a straight line, in order to have momentum, I have to be moving and with a certain mass. Now let's change that to rotational motion. I'm going to use a different letter, L. And I'm not just interested in its mass, but rather how is the mass distributed? We know from a previous video that it's not the mass, but rather the moment of inertia, and we give that the letter I. So that ends up being I equals the sum of mass times its distance from the center squared. You can see in this case, because I have some of the mass farther from the center compared to this one will have a larger moment of inertia than this one. And then instead of having just a velocity, I'm going to have an angular velocity, so I use the letter omega rather than the v. Depending on how fast it's spinning will depend on how much angular momentum I have. So if you take IB Physics, this is the data booklet equations we have for the exam starting in May 2025. And here is the one I just derived for you for rotational motion. If you look really closely, here's the moment of inertia one I was just talking about. And all of these are just our suvat, our normal kinematic equations, but they're for angular rotation. The other thing I'll point out is if this is angular momentum, then delta L must be the change in angular momentum, and we know that that's just called impulse. Just like we had a impulse in linear momentum, we also will have a impulse in angular momentum. One of the big things we use in linear momentum is the conservation of momentum, and there's no change when we're talking about things rotating. So if I want to translate this into rotational speak, the total angular momentum of a system is constant, providing there is no external torque acting upon it. Remember, instead of saying forces, now we're going to talk about torque. And for those of you who are not as familiar, torque is just the idea of a force acting at a certain distance in the center of the rotation. Again, you can see my other video on torque if you need to watch that as well. So if we have here, most people may have seen figure skating before, and earlier I said that this picture here had a larger moment of inertia than this one. So if this figure skater brings their arms in closer, like in this case, that means their moment of inertia will decrease. Remember, momentum is moment of inertia times the angular velocity. So if their moment of inertia decreases, that means the angular velocity will have to increase. So if they start off in this position and they bring their arms in closer, decreasing their moment of inertia, that means the angular velocity must increase and they'll start to spin faster. So you'll see a lot of spin moves in figure skating where they change the position of their hands or maybe their legs in order to change the rate at which they're rotating. You will also see this in terms of diving. This is called the tuck position where you have your legs in close, and it's different than the pike position where they bring their legs in but they're straight. Now, when you bring your legs in closer to your body, again, you're going to reduce the moment of inertia. And in this case, compared to this one, you can see that the legs are not brought in closer. So if they want to spin faster, you'll see them separate their legs like this to bring their legs in even closer. So if a diver isn't able to do a certain number of somersaults during their spin, they'll typically learn to pull their legs farther apart and in closer to make sure they can do their double, triple, whatever it is number of somersaults they want before they hit the water. Here's another thing that we've done in linear motion that we're going to now move into angular motion, Newton's second law. Now, lots of people want to just say F equals ma, but remember that's not really how Newton said it. This is only true if the mass is constant. He actually said that the net force is equal to the rate of change of impulse, which is this. If I then separate this, if mass is constant, then only the velocity is changing, and here's where we get our acceleration. But we know at this level that it could be the mass changing at a constant velocity. For example, a water truck dripping water out as it's traveling down the road. Now, the letter J just stands for the change in momentum. So this is the general form. My equation here just rearranged. My J, the change in momentum, equals the net force times the time. That's what I have here. Again, reminder, this is a net force. If I translate that into rotational motion, I have change in L instead of a change in P. So there's my impulse. Instead of force, I have to have torque, and time does not change. I can also use the equations for torque being force times the radius from the center, and the moment of inertia being mr squared. I can combine these as well to be for a single point source, the change of momentum being I moment of inertia times the angular velocity. Now that we've gone through the theory, and before we get to the questions, has this helped you? Consider helping me out by telling your friends about the videos. Consider subscribing or liking the video. Thanks for your help. So let's use an example. A young child runs towards a playground merry-go-round, like I have in the picture here. It's at rest, jumps on the edge, and the child's speed is originally 4 meters per second. Assume she lands at a tangent to the edge, which is at 1.5 meters, and the merry-go-round has a moment of inertia of 100 kilogram meters squared. So we don't have to calculate it, it's already given to us. What is the angular speed of the merry-go-round after she lands? Okay, one of the things I'm going to need here is I'm going to be solving this with the conservation of momentum. Even though this is angular momentum, I'm going to do it the exact same way I would do it if it was linear momentum. So I'm going to say conservation of momentum here, and I'm going to do it before and after. And one of the things I'm going to need in order to do this is I'm going to need the moment of inertia of the child as they're sitting out here at the edge. So let me just go and calculate this first to make our lives easier. And it's going to be mr squared. So their mass is 25. The radius that they're at is at 1.5 squared. And that's going to give me a value of 56.25. I'm going to keep the extra decimal places for now. And that would be in kilograms meters squared. So let's set up our equation here. When we start, the actual merry-go-round does not have any angular momentum, but the child does. So that will be 56.25 moment of inertia times their speed, which is 4. And afterwards, we'll have the moment of inertia of the merry-go-round, which is 100, and the child, 56.25. And we're looking for its angular speed afterwards. If I rearrange this and pick up my handy-dandy calculator, I get 1.4 radians per second. So what looks like a big, difficult question to set up with isn't too difficult. I need to be able to calculate the moment of inertia. That would typically be a mark here. I would typically get a mark for setting up the conservation of momentum, and then one more for the final answer. Okay, on to example 2. A rope is attached to a rotating cylinder. I've got the mass and its radius. They've also given here how to calculate its moment of inertia. An increasing torque is applied as shown in the graph. What is a change in angular momentum? Okay, so first of all, you might be saying, okay, I'm looking for change in momentum, and I see this equation in my data booklet. Change in momentum is tau and time. And I've got a tau and a time here. Now the problem is, which tau would you use? It's not a constant torque. So in fact, you really shouldn't be using this equation for that reason. But if you recall, if I had a force versus time graph, the area underneath the line would give me the impulse. So if I get the area under this line, this will give me my change in angular momentum. And it's just a triangle, 1/2 base times height. And that will be 1/2 times 2 times 2, which will give me 2. Okay, so there's my answer here. The units will be newtons, meters, seconds. B, if the cylinder started from rest, okay, so that means omega I will equal 0. What is the final angular speed? That's omega F. That's what I'm looking for. I'm missing a lot of information here, or so it seems. Well, we also have the equation delta L equals delta I omega. And in this case, the I is going to be constant because we don't have anything changing about our cylinder. So it must just be the omega that's changing. So we know our change in angular momentum was 2. Our moment of inertia is going to be 1/2 times the mass, which was 2.5, times the radius, 0.75 squared, because I'm just using this equation right here. And our change in omega will be just the final one, minus 0, which I'm not going to leave there. Now I'm going to rearrange and pick up my handy dandy calculator, and I'm going to get 2.8 radians per second. Please read the success criteria one more time. I hope it's helped you, and if it did, please consider giving the video a like and telling your friends about it. Thank you!